Yeah, thank you very much. I'm very happy to be here and online and telling you about this topic, which is very close to my heart. So I'll be telling you about this thermal EFT and universality of Rényi entropy and CFT. And so thermal EFT is basically an effective field theory which kind of systematize the various behavior of physical quantities in high temperature limit in conformal field theory. And most of the time we deal with some OP coefficients or thermal partition function and so on. But in this talk, I want to convey this message that even if we look at some quantum information motivated quantity like Rényi entropy, which is apparently non-local, even in that case, there is some universality, and those universalities can be explained and explored using the same kind of thermal EFT. So we'll be seeing basically two quantities in this talk. One quantity is the thermal partition function, and because it's an EFT, it will come with some Wilson coefficients, and we will see the Rényi entropy, and we will also see there is an effective field theory description of this Rényi entropy. It will also come with its own set of Wilson coefficients, and the idea is to show that the same Wilson coefficients actually control the high temperature physics and also the Rényi entropy in the Rényi index going to zero limit. So that's more or less the broad picture of this talk. So please feel free to ask questions, and I want to make this talk very pedagogical and broad brush. So without much ado, let's start. So so this talk will be based on this paper that we put out with Yue and Hiroshi, and there are some like recent reincarnation of thermal EFT by people at Caltech in these two papers. So the basic idea is to use some of the techniques available in these papers and employ it in the context of Rényi entropy. Okay. So the plan of the talk is following. So first I will start with a very broad overview of what we mean by universality in CFT, why can we even expect some universality in the context of CFTs? And then I will explain the formalism of thermal EFT, or how one can set up an effective field theory to describe the high temperature behavior. And then finally, I will come back to this Rényi entropy business and use this thermal EFT in the context of Rényi entropy. Okay. So let me start with a very broad question. Like, suppose someone hands over you with a quantum system. What is the most basic yet powerful question that you can possibly ask about this quantum system? And of course, the first thing you want to find is find the spectra of the Hamiltonian. In some sense, if you are super powerful and if you can diagonalize the Hamiltonian, if you know all the energy spectra, then basically you are done. You know all the things you are supposed to know about the system. But in practice, it so happens that most of either the quantum systems are strongly coupled, or we are dealing with some system with enormous number of particles. So oftentimes it's just impossible to diagonalize the Hamiltonian. Like even you cannot even imagine putting it on a computer. So that means we have to be more like creative, and we have to find other ways to understand the spectra of the Hamiltonian, find the patterns in them, find some universality. So that's where this whole story begins, that we want to use some symmetry property, some consistency property to understand the spectra of Hamiltonian, maybe not in all gory details, but some pattern. So with that motivation, so basically we can the natural thing we can ask that what do the asymptotic spectra of a Hamiltonian look like at some large energy or large speed? And you can make this question more detailed. For example, you can ask whether the spectra looks like this three of this kind. For example, whether this has a very large gap. Oops, something happened. Okay. Whether this has a very large gap, whether this has a regular gap, or whether the spacing goes to zero. And it turns out oftentimes in conformal field theory, you can really answer these questions, and the symmetry kind of constraints what kind of behavior is possible in given a system. So, and these kind of questions are not only for academic purpose, because like it goes way beyond academic purpose, because the asymptotic spectra of a quantum Hamiltonian reveals deep insights about various thermodynamic properties at high temperature. For example, if you want to know heat capacity, if you want to know some other properties of the system when you heat up the system, then you want to know about the high energy behavior. Because it turns out that as you heat up the system, you can access more and more higher energy. So basically the high energy density of states or the OP coefficients at some high energy states would control the behavior of the system when you heat up the system. And also it kind of tells you that the nature of the dynamics, whether the system is chaotic or integrable, it kind of gets imprinted in the spacing. Because for example, in a chaotic system, you would expect the spacing actually goes to zero as you go to very high energy or very high spin or some high quantum number, because more or less all the phase space gets explored in a system which are expected to thermalize. And in the same way, like if you want to look at thermalization at the level of a subsystem, then also these kind of questions are very important to understand, like what is the spectra of the Hamiltonian at very high energy. So the upshot is these kind of questions are important, and they have some very deep physical imprints. So as I was saying that if you just give me some arbitrary quantum system, it might be a bit hard to answer this question. So we will restrict our focus on conformal field theory. So you can view this in two ways. One is that conformal field theory has a lot of consistency conditions. So the CFT observables satisfy various non-perturbative consistency conditions. And then we can use this machinery of conformal bootstrap, which basically tells us that the observables are highly constrained, and there lies the universality. And another way of viewing the same thing is that like you can like conformal field theory gives you an organization principle in the space of all the theories. So is the conformal field theories are kind of a lamppost in the space of theories. And then if you can understand the universality appearing in the conformal field theory, that kind of gives you some handle on how various universality emerges even away from conformal field, like the fixed point or the CFT point, at least in some sense of conformal perturbation theory. But today in the talk, we will entirely focus on conformal field theory, and the idea would be to use various kind of consistency conditions to figure out the universality that appears in the spectra of the Hamiltonian and eventually in the context of Rényi entropy. So the basic question that we are asking here, that given a conformal field theory, what do the asymptotic spectra of a Hamiltonian of the CFT look like? And as an aside, I should also mention, so I will not mostly talk about holography in this talk, but I should just mention that all these questions has also implications in terms of holography, because high energy states in CFT via IDS CFT tells you that it captures the black hole physics. So whenever you are answering some question about the asymptotic spectra of a CFT, it basically provides you insights into the quantum nature of the black holes. For example, it can tell you the entropy of a black hole, it can tell you the physics of the near extremal black holes, and it can also, for example, tell you that suppose you are given a gravitational path integral, you can ask in that putative gravitational path integral whether the black hole dominates, whether some other geometry dominates. And all these kind of questions can be translated in a question of a CFT. And eventually it can be turned into a question about a high energy state in a CFT. And then you can ask whether the universality in the high energy states in the CFT help us answering this question. And it indeed does. So, so a classic example of such kind of universality is the Cardy formula. So what does Cardy formula tell us? It's basically a statement about 1 plus 1D or 2D CFTs. And in 2D CFT, that you like the CFT comes with a central charge. So central, you can view the central charge in various ways. So one way of viewing this is it's like if you take a CFT on a circle, then you can compute the ground state energy of this CFT. There would be some Casimir energy because it's a compact space, and this Casimir energy is related to minus C over 12. So central charge in some sense parameterizes the ground state energy. And also it appears in the Virasoro algebra, which is the symmetry algebra of 1 plus 1D CFT. It also appears in the stress energy tensor correlator. So C is an important quantity, and it in some sense it characterizes the 2D CFTs. And this Cardy formula basically tells you that if someone hand me over a central charge, I can immediately tell you that how the density of states behave at very large energy or large delta. And it will be given by this formula where you can see there is exponential growth and there is a prefactor. And whenever I am saying that the result is universal, it basically means that it doesn't really matter what kind of CFT I am looking at, what are the intricate details of the Hamiltonian, whether there is interaction or not. As soon as you give me this number C, I can write down this formula and it is controlled by a single parameter. So whenever I am saying universal, basically in this talk, I mean that it will only be controlled by a single parameter or some few 2 or 3 parameters. Like it will not depend on the whole details of the CFT spectrum. Okay. And then you can also ask about a refined version of this formula. That so you may ask that, well, we know the density of states is really a distribution, so how can we approximate with a smooth function? And of course there is a refined version of this which basically puts some inequality of this form. So for this talk, this thing is not very important. I just want you to mention that whenever I will be mentioning about some formula for density of states in context of Hamiltonian or in context later in context of Rényi entropy, there will be some inequality of this form I have in mind. And in context of 1 plus 1 DCFT, you can make it completely rigorous and you can write down some precise inequality of this form. In higher dimension, this is not entirely possible, but conceptually something like this should exist. And just to tell you briefly what this means, so here you're basically on the numerator, you are counting the number of states in some particular window where it is centered at delta, and the width is twice delta. And in the denominator, this rho zero function is basically the average Cardy density, which is this Cardy formula. And roughly speaking, you would expect that this actual count divided by the Cardy density is like would be of the order of window size. So you would expect it would be of twice little delta. And what you can do by doing some rigorous analysis, you can show that this is actually upper bounded by this quantity, which depends on window size, and lower bounded by again this quantity, which is again depends on this window size twice delta. So whenever I will be saying something about asymptotic spectra of some quantity, some operator, I will mostly be focusing on this kind of formula. But in the back of my mind, you should always expect something like this should exist. Okay. Is there any question at this point? Okay. If not, let me move ahead. And then the point is that in 1 plus 1 DCFT, the way this formula is derived is using modular invariance. And then you can immediately ask whether such formula exists in higher dimension. And of course, in higher dimension, we do not have any modular invariance because, well, in 1 plus 1D, the modular invariance appears because you are thinking of a CFT on a circle. So you have a S1, and then there is you are thinking of a thermal CFT. So there is another S1. So in 1 plus 1D, basically you have S1 times S1, and you can swap these two S1s, and that leads to the modular invariance. But in higher dimension, what happens in higher D, you basically look at S1 times SD minus 1, but now there's nothing to swap because there is no two S1s. So that basically leads to a scenario where there is no modular invariance. And then basically because there is no modular invariance, you may want to ask whether there is some universality or not. But the point is that even without the absence of modular invariance, we have something called thermal EFT, and we can use this thermal EFT to show that such universal formula exists. So in some sense, in 1 plus 1D, so CFT, you can also derive the 1 plus 1D CFT formula using this thermal EFT. The modular invariance in some sense buys you more. It also gives you some control over the non-perturbative corrections. So in the thermal EFT, you can write down some non-perturbative corrections, but mathematically it's under less control compared to 1 plus 1D CFT. And this is kind of a abstraction to proving some formulas like this in higher dimension. But again, as I was saying, that today in higher dimensional case, we won't be attempting to be super rigorous like 1 plus 1D. So we will stick to this business of thermal EFT. And just a historical comment that so this thermal EFT has been reincarnated in these papers in recent times. But if you go long back, then there is this papers by Siraj and other people from TIFR India. And there basically they have some description in terms of hydrodynamics. And essentially this idea of hydrodynamics and to describe the high temperature behavior and the idea of thermal EFT is conceptually kind of similar. But I will stick to the notion of notion of thermal EFT as introduced in these papers because I am more familiar with the recent ones. Okay. So now, as I was saying that we want to understand the high energy behavior of the Hamiltonian. So that immediately means that we should look at the high temperature behavior of the the system. And that basically means we should look at the high temperature behavior of the canonical partition function. And as I was saying, thermal EFT is basically a tool to describe this high temperature limit. So it kind of systematize like how would you characterize the behavior of the partition function, the behavior of the free energy, or behavior of any beta derivative of the partition function as beta goes to zero limit. So now before going to the Rényi entropy case, I would like to give you a quick derivation of the asymptotics in 1 plus 1D CFT. And I am giving you all these flavors of how we derive things in the with the actual Hamiltonian, with the motivation in mind that at the end of the day we are going to apply these same techniques in the context of Rényi entropy. And then you will see that once I make the connection of the Rényi entropy with this thermal partition function, once this connection is made, then I can easily implement all these techniques that I have been explaining to you right now. So the derivation of the asymptotics in 1 plus 1D CFT goes like in the following way. So basically you have this partition function on, oops, what happened? You have the partition function on this side. And then you want to ask what is the behavior in the beta going to zero limit. And suppose someone tells you the beta going to zero limit is given by this quantity. So either you can derive it using modular invariance. For example, claiming z of beta is z of 4 pi square over beta. Or you can derive it using thermal EFT, which I am going to explain soon. But for now, suppose someone tells you this beta going to zero limit of this partition function. And then the claim is that once you know this equation, you can immediately derive sorry d of e, the degeneracy, as e goes to infinity. And the way to do this is following. So you first write down this sum as an integral. So this is basically a Laplace transform. And the point is the Laplace transform of density of states in the beta going to zero limit has this universal behavior, which is again controlled by a single parameter, which is C. So now once we have this expression, we can extract the density of states basically by inverting this formula by doing an inverse Laplace transform. So we do the following. So we start with here, we write down an expression for density of states, which is an integral along the vertical line. And then the point is this integral can be done using saddle point analysis. So basically we do the saddle point. So this is the saddle point for beta. And in some sense, this kinds of relates the quantities in the microcanonical with the canonical. So this is a canonical quantity, and this is kind of a microcanonical quantity. So another way of saying the same thing is that this analysis kind of establishes the equivalence between the canonical and the microcanonical ensemble. So evaluate this integral with the saddle point. If you evaluate, if you evaluate the integrand on the saddle, this will give you the exponential growth. And then there will be like Gaussian fluctuations around the saddle, and this prefactor will come from the fluctuations. And that's how you will derive the high energy states, the density of states, using 1 plus 1 DCFT. And this technique is very general. In some sense, instead of 1 plus 1 DCFT, if someone gives you the analog of this equation here in higher dimensional CFT, you can again do the same trick. You can write it as a Laplace transform of density of states. You can do an inverse Laplace, and that will immediately give you a density of states. So our main job is to figure out that what is the analog of this quantity in higher dimensional CFT or in the context of Rényi entropy without having something like this. Because again, in higher dimension, we do not have the modular invariance. So we need to be more creative to figure out the analog of this quantity. Okay. So just to give you so what we have learned so far, that we have this conformal field theory. We are using this consistency condition either in the form of modular invariance or thermal EFT. And then the idea is to show that this basically makes the observables highly constrained, and there is an emergence of universal features. So given all this setup, now basically we have all the motivational background, like what we did with the usual Hamiltonian, with the usual thermal partition function. Now basically I come back to the original question of the universality of Rényi entropy. So you ask that, well, I have my conformal field theory. I know there are universalities in the spectra of the Hamiltonian, but what about various non-local quantities? What about quantities which are basically motivated by quantum information? And in particular, you can ask, what do the asymptotic spectra of the entanglement Hamiltonian looks like? So what is this business of entanglement Hamiltonian? So this is a fancy way of writing about density matrix. So, so the setup you should have in mind, that suppose you are given a CFT on some compact space, and then you are considering some subsystem, and you are accessing that subsystem. And one way to describe the fact that you are only accessing the subsystem is to consider a reduced density matrix. Sorry. So, so suppose you have a CFT, you divide it into two regions, A and A complement, and then formally you define this, and then you want to learn about this row of A, and you can write down this row of A as formally as e power minus proportional to some e power minus k. This is possible because we know the density matrix has trace 1, and all the eigenvalues are positive. So you can take log, and this operator k is well defined. And this operator k is known as entanglement Hamiltonian. So in some sense, if you know the spectra of the entanglement Hamiltonian, you have all the information about this density, matrix. So earlier I was telling you, I started with a basic question that given a quantum system, what is the most fundamental thing you can ask? And the question was what is the spectra of the Hamiltonian? And here the analogous question in the world of quantum information is that, suppose if someone hands you over a density matrix, then it's equivalent, like if you want to learn about this density matrix, is equivalent to knowing or learning about this entanglement Hamiltonian here, k. So the question I will be asking, so the next question you can ask, what is the spectra of the entanglement Hamiltonian? Again, of course, it's very hard to compute all the spectra of the entanglement Hamiltonian or diagonalize it. So you resort to this question that what is the asymptotic spectra and whether there is some universality in the asymptotic spectra of this operator K.
Can I ask a naive question from someone that knows nothing about it? Like, why would it be easier to work with this fake Hamiltonian you have built by exponentiating than rather working directly with the reduced density matrix? Like, why
You
is
can,
that better?
yeah, you can also, like, you can forget about this entanglement Hamiltonian and you can ask what are the distribution of the eigenvalues of the density matrix. That's a fair point. But the reason I want to write it as e power minus k, because I have in mind the thermal partition function, which goes like e power minus beta h. So
Okay,
I want to draw an analogy between e power minus beta h and e power minus k.
okay.
And because of this analogy, you will see that whatever we are doing with the thermal partition function, all of these technologies go over in asking the spectrum about the spectrum of k. So that's the idea. And then once you know the spectrum of k, you can also translate it back to the eigenvalue distribution of rho. So at this point, um, it's just a trick to have the similarity with the thermal partition function. And I should mention one more point. So normally, like, so the k is basically defined as minus log rho. So K is basically naively you would expect K is a horribly non-local object because density matrix is a path integral over a lot of, and in fact it is true. Like for most of the cases, K is a horribly non-local object. You cannot write it as an integral over local stuff, which is very different from the actual Hamiltonian, because actual Hamiltonian of a system can be written down as an integral of stress energy tensor. But it so turns out that there are various like spatial geometric configuration. Like for example, if you consider a spherical entangling surface, then there are theorems in quantum information which tells you that this k can indeed be written down as some integral of the of some local operator. In fact, in some case, k is like a boost generator. So, so the original reason why people came up with this idea of entanglement Hamiltonian, because they, in this, for example, in the spherical entangling surface, people wanted to use this fact that K can be written down as integral of some local operator. And for example, there are famous proofs of NAC and all these things, which actually relies on the fact that K can be written down as an integral over stress energy tensor, and then sorry, integral over some local operator involving stress energy tensor, and then you can use some information about stress energy tensor OP and so on. So all I'm trying to say that there is also other motivations behind introducing this K, because in some cases K reveals the property that it can be written down as integral of local operator. Okay, good. But for this talk, I guess this is just to maintain a similarity between e power minus beta h, e power minus k. And this is precisely my next slide. So here we have two things. So on the left side, we have the asymptotic spectra of the Hamiltonian, which I spent quite some time. And as I was telling you, that we compute the canonical partition function in the beta going to zero limit, there is some universality. And this universality immediately tells you the asymptotic spectrum of H. So we will do something similar here. So I will start with rho, which is a density matrix, which is like e power minus k. So I will try to compute this trace e power minus n times k in the n going to zero limit. So this n will play the role of beta here. And the idea is to find something universal in the n going to zero limit. And once I have this universality, I can again do the same trick of inverse Laplace to figure out the asymptotic spectrum of k. So is this slide clear? I think this is one of the most important point here, that we have some structural similarity on both sides. And because we have structural similarities on both sides, I can, if I know how to handle the left hand side, I can easily like develop techniques on the left hand side and use this on the right hand side, is the because it has the same form. Okay. So now in the rest of the talk, I will be first telling you how to go from here to here, how to figure out this universal behavior. in the context of thermal
Maybe
EFT.
one
Yeah.
concern, like,
Yeah.
how do
Yeah.
you know that you can actually perform the Laplace transform? Like, you need to have certain decay properties, and since this k is potentially extremely horrible, you
Yeah,
have
yeah,
to
yeah.
take a
So
leap of faith.
yes, that's a good point. So, like later, as I will show that this in D dimension, this universal behavior goes like something like this, and here this also goes like something like this, and then you can do a inverse Laplace in the sense that you can again do this saddle point approximation, and in D equals to it exactly becomes 1 over beta, which I just showed you in 1 plus 1D. So yeah, and the whole point is that this leading behavior is kind of controlled by the EFT, like it cannot be something else under some certain assumptions that I'm going to explain. I haven't yet explained. Okay, so now let me explain you the thermal EFT side. So basically I'm going to explain you how to derive the universal formula in on this side, and then I will come on this on the right hand side. So the idea of thermal EFT is, as I was telling you, that to figure out the z of beta in beta going to zero limit, and one way of thinking about z of beta is basically it's a partition function on this manifold, which is sd minus 1 times s1 beta. So you have a sphere, and then on the you have a thermal circle. So to find this partition function, it is more useful to couple the theory with a curved background. So instead of sd minus 1, you basically start looking at some manifold which is sigma d minus 1 times s1 beta. And then you write down a metric on this manifold which is of this form: gij dxi dxj. There is a dilaton, there is a d tau minus a square. And this a basically tells you that, like, as you go along the time circle by beta amount, there might be some twisting, like how you identify. So it might happen that as you go tau to tau plus beta, one of the angles in the sphere gets rotated by some amount, and that rotation part, which mixes the tau and the x, is taken care of by this a. So a is basically ai dxi. So now the idea is that, so you have this metric, so you couple the CFT with this background metric. Now you are basically taking beta going to zero limit. Now the idea is that in the beta going to zero limit, the circle basically shrinks, and then you would assume you would expect that if you are dealing with an interacting CFT, it will create a thermal mass gap as you take beta going to zero. In fact, for example, in the free scalar field, you will see that the mass gap goes like 1 over beta square or something like that. So as beta goes to zero, it creates a large gap. So basically it tells you that in the beta going to zero limit, this should be described by a gap theory, z gap, and this theory will only depend on local functional living on this manifold sigma d minus 1. So it will depend on z ij, ai, and this dilaton phi.
So may I ask you a quick question again?
Yeah.
I'm a bit confused between you've wrote sigma and then
Mhm.
direct product S1, but then the metric you're writing is kind of a non-trivial vibration.
Yeah, yeah.
So
Yeah.
so the S1 is so the metric you wrote is for the
Oh, I see.
direct product you
So
wrote?
yeah. So I should be careful. So this cross is not really an Cartesian product.
Ah,
So
okay,
it's
okay,
like,
fine.
so the way you should imagine it, that
Yeah,
as you go up in the tau direction by beta amount, you
yeah.
rotate the sphere by a little bit and then identify.
I see.
So
So it's really like a S1 that's twisted
yeah. So
inside the
for
bigger
example, in
manifold.
yes. For example, in 1 plus 1D, it will basically denote a torus which is like tilted. So,
Yes.
so as you go up, so this line and these lines are identified. So
Mhm.
as you go up in the tau direction by beta, you basically tilt the circle a little bit. Okay. Yeah, so Yeah, this cross is slightly misleading, but that's what I meant. So in the beta going to zero limit, so the theory becomes gapped. So the idea is that you can write down an effective action which only depends on the fields living on this sigma d minus 1. So, and these fields are basically Gij, this dilaton field, and this A field, which only depends on sigma d minus 1. Now, you also realize that there you have a conformal symmetry for like you are dealing with a CFT. So somehow you have to use that fact that you are dealing with a CFT, and that basically means you have Weil invariance. And that basically tells you that you can set this phi to 0. So you can use Weil invariance to say that this is Z gapped G hat Ij AI 0, where G hat is some e power minus 2 phi times G. And of course, if the CFT has some Weil anomaly, there will be some Weil anomaly term, but these Weil anomaly terms are always subleading in the beta going to 0 limit. You can keep track of them, but for the purpose of this talk, they are very subleading, so I will not be worrying about them. But in the paper that, like in the two other papers where we talk about thermal EFT, there we have taken care of all these anomaly terms also. Okay, so now you have this G gap, and now you can write it down as e power minus S thermal, and S thermal only depends on this Gij and AI. So now all you need to do, you need to write down all possible terms which are invariant with this constructed out of this matrix Gij and this field AI, which are gauge invariant and which are scale invariant. And then it's easy to easy to write it down. So let me go over here. So the first term you can possibly write down goes like d minus 1x square root g hat times some Wilson coefficients f, for example. And the second term you can possibly write down is c1 times r hat. Then the third term you can write down c2 f square and so on. And where the f square is built out of this gauge field AIs.
I'm still bothered by the metric. Can I ask
Yeah,
another
yeah, yeah,
question?
yeah.
I'm not understanding because you can non-trivially fiber like in a larger sphere, like in a kind of Hopf vibration. So
Mm-hmm.
why do you need to have like, because this metric Gij can be anything for you as long as it's curved, and you can put an S1 inside it.
Yeah, 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 yeah.
So, but why can't you just say that you have like a bigger sphere in which you have an S1? Is because you will be able to be more general, or is like I'm
Oh,
a bit motivation with this leap that you're making. Why not
oh,
stay in
so
the sphere?
I guess you should view this sigma d minus 1. So you should always think of this in the following way, that we are taking a CFT and we are coupling it to a background,
Mm.
and the background metric can be written down in this Kaluza-Klein form.
Okay, okay, okay. So you're
And
going
so,
slightly outside the theory you were before.
yeah, yeah, but then the is yes, but the point is SD minus 1 times S1 can also be written down in this form.
Yes, exactly. But that's my point. Like, why don't you just not restrict to SD minus one
Oh, I see.
solution?
Yes, I will explain you soon. Soon.
Ah,
Just
okay,
give
okay.
me a
Sorry,
couple of
sorry.
yes,
Thank you.
yes, yes. Yes, I think that's an excellent point. Why I am going beyond. So I am going beyond because of the following reason. So now you see I have this expression here. Now there are some Wilson coefficients AF, C1, C2, and then there are some geometric quantity which is this G hat, R hat, F, capital F, so on. So now you see that I have disentangled the contribution coming from the CFT. So this you should view this AFC1, C2 as some intrinsic CFT quantity. So if I change my CFT, all these Wilson coefficients will change. But all the other dependents will remain same if I stay on the same geometry. So now the point is, now I have this action. Now I will evaluate the above on SD minus 1. So now I can put the metric in of SD minus 1 here. Then I will, like, I can do all this integral and there will be some expression. But the point is that now suppose instead of SD minus 1, if you start with some other geometry, say hyperbolic manifold, then this f c1 c2, this will all remain same. The only thing that will change is these evaluations. So that is the reason why I went away from SD minus 1, because I wanted to pinpoint the fact that there is some geometry dependence and there is some CFT dependence. The CFT dependence comes with these Wilson coefficients, and the geometry dependence comes with this r hat f and this square root g. So this I wouldn't have explored this universality if we only do the SD minus 1. Is it clear? Okay, great. So we have this thing. So for example, you can evaluate it on the sphere and you can get some expression. So for example, if you do it in 2D, if you, how much time do I have left?
In principle, 20 minutes, but we don't have such restrictions.
Okay, I think I will be done in 20 minutes.
Okay, perfect.
Yeah. So if you do it in 2D, then you will see that this f is actually related to twice pi c over 12. And all the C1, C2, these things actually goes away. There is no zero. And in particular, the thermal action with, like, if you evaluate everything, this will look like 1 over beta twice pi C over 12 times L in 2D. That just comes from evaluating this 1D integral, because it becomes dx, it's just a circle, so that gives you an L. There is a f. And you might ask how the beta dependence comes in. The beta dependence comes in because there is a dilaton here in phi, and this dilaton keeps tracks of how the powers of beta goes in. So if you evaluate all of these things very carefully, then you will see that uh, the structure of this thing is of this form. Like, you start with 1 over beta to the power d minus 1. Then roughly speaking, it goes like f plus C1 some number times beta square, C2 some number times beta to the power 4. Sorry, this is also beta square, and then some other pieces. So it's an expansion in beta, in the beta going to 0 limit. And this expansion is kind of, for example, intuitively you can see it. For example, this thing goes like power of d minus 1. So to match with this power, you should have beta to the power d minus 1, just naive dimension analysis. So in some sense, this EFT is a more sophisticated version of dimension analysis, where you keep track of the Weil invariance and other things. Well, in general, I think this is true that any kind of EFT that appears in physics is a more sophisticated version of dimension analysis. So this is also not a different than that. Anyway, so again, the lesson is that we can disentangle the information of the CFT and the information coming from the geometry, and we will be going to use that in the context of Rényi entropy, because in the context of Rényi entropy, the manifold will not be SD minus 1, something else. Okay, so I do not need to use this page. So this is the upshot, as I was saying, that this is the thermal effective action. And if you do not have any angular fugacity, which basically means that if you do not rotate the sphere as you go tau going to tau plus beta, then you can set AI to 0, which basically means F to 0. And then the leading term basically goes like this, which is beta to the power 1 minus d times the volume of sigma d minus 1. And as I was saying, in 2D, the F is related to central charge. In particular, F was twice pi c over 12. So is there any question from the thermal EFT side at this point? If not, I will then go ahead. Okay. So I already explained to you the left hand side, which basically is the, like, if I use the thermal EFT. Now I'm going to explain you the right hand side. So, so what do we need to do? So sorry, as I was telling you that that this this k might be some horribly non-local stuff, but the idea is to understand, the task is to understand k as some Hamiltonian and trace as computing some partition function on some sigma d minus 1 times s1. So given a density matrix, we want to interpret this k as some Hamiltonian, and if we can do that, if we can somehow interpret the computation of trace in e power minus nk as some sort of computing partition function, then we are basically done, because we know how to compute the thermal partition function on this kind of manifold. And to our advantage, this mapping has already been done in literature by Cassini, Mayer, and Huerta in this famous paper. So basically, for concreteness, we can consider a spherical entangling surface, and it turns out for the spherical entangling surface, you can do some conformal mapping, and by mapping this, you can relate this k this entanglement Hamiltonian as some actual Hamiltonian on this kind of manifold, where hd minus 1 is basically the hyperbolic space. So this is hyperbolic space. So, and this mapping is done. So basically you start with a flat space, and then you do some change of variable, which is explained here. And once you do this change of variable, you can write down the metric in this form. And you can also show that the time period is related to twice pi Rn, the Euclidean time period. So this is your effective beta in this context. So this mapping and how this happens is kind of intricate to explain. So let me give you some rough intuition of why this is true, like why we can relate the density matrix with some thermal partition function on this manifold. So just imagine about the Unruh effect. So for example, suppose you have this kind of space, and suppose you have an accelerated observer here, and for the accelerated observer, it can only access the right Rindler wedge. And we also know that this accelerated observer on the right Rindler wedge basically views a thermal density matrix, because the vacuum becomes thermal from the point of view of this accelerated observer. The another way of saying the same thing is that if you take a full density matrix, if you take a vacuum on this full slice here, and if you reduced it onto the left wedge, then this reduced density matrix will be thermal with respect to this accelerated observer. So another fancy, so this classic, so a fancy way of explaining this classic Unruh effect is to say that the density matrix supported on the right wedge is basically e power minus k, where k is really the boost generator which makes the observer accelerate. So here is the scenario where k is really an integral of a local operator, and there is a physical interpretation that k is a boost. Now, if you remember the classic Unruh effect, then you can go to this Rindler coordinate, and in the Rindler coordinate, the boost really becomes a time translation in the Rindler time. So this is a scenario where you start with a density matrix where you have e power minus k, and k is the boost generator, and then you do a change of coordinate, go to the Rindler coordinate, and in the Rindler coordinate, this boost becomes time translation. So from the perspective of Rindler coordinate, you are really evaluating a thermal density matrix where the time translation is generated by the time translation in the Rindler coordinate is generated by the k. So this intuitive picture kind of goes through in the higher dimension, and this is basically the content of this paper where they chart out this map. So instead of going over to this Rindler coordinate, you do this complicated mapping, and then basically the analog of the Rindler coordinates becomes this hyperbolic space. And then there is a tau coordinate. So the point is that So in the original space, you have a spherical entangling surface, and the modular Hamiltonian, or this entanglement Hamiltonian, gives you the causal development of this spherical entangling surface. And once you do this coordinate transformation, then this causal development of the entangling surface becomes time translation in this hyperbolic space. So the upshot is that the reduced density matrix in original coordinate becomes thermal density matrix on this hd minus 1 times s1. And once you have this map, then you already know how to apply the thermal EFT on hd minus 1 times s1, because I already explained to you that it's not important that we are stuck with sd minus 1 times s1. I can take any sigma d minus 1 times s1, and I can use the thermal EFT. The Wilson coefficients that appears, they stay same. So for example, the Wilson coefficients that appear here, they stay the same. I only need to evaluate now this R, F, and G on the hyperbolic space. And this is why the same EFT, that this is why I'm keep on saying the same EFT, the same Wilson coefficients controls these two apparently different kind of quantities. Like, to begin with, there is no reason for them to be same, because one is talking about thermal partition function, one is talking about some Rényi entropy, some non-local business. But because of thermal EFT, it turns out the same coefficient appears in both calculations. And then you can go ahead, and people have computed the holographic Rényi entropy, and then you can compute this F for holographic CFTs by computing the thermal density matrix for the the thermal partition function for the holographic CFT. And you can also compute the Rényi entropy for holographic CFTs, and you can indeed show that this F matches in both computations. So without the thermal EFT, this would have been almost a magic, that there is no reason for these two coefficients to match in these two different computations. But because of thermal EFT, it's kind of now apparent that why the same coefficient appears into entirely different computations. Okay. Now, yeah.
Maybe I'm too fast, but may someone be bothered that the Ricci scalar will be positive and negative in this case?
Yes, that's a very good question. I was expecting this question. So yeah, so I think one should be slightly bothered, but I think there is a way to define this. So because these are CFTs, we are good, because so this hyperbolic metric is while equivalent to flat metric. So the idea is that one can define the CFT on the while on the flat metric, and there is no issue. And then there is a what like you do a while transformation. And so I think a proper way to define this CFT on this kind of manifold is to do this while transformation and define in terms of the flat CFT data. But at this point, these are words. I like at the level of EFT, there is no red flag, nothing bad happens. But I think it would be nice to understand this in a more rigorous way, that like you can forget about all these EFTs, you can just ask a very simple question that can I define a CFT on hd minus 1 times s1 in a very clean way? And one way to go about to do is to use this while while invariance and transform it from the flat space. Yeah, but I think that's an interesting question and worth in more investigation than what I am telling you right now.
Okay, I see. Okay.
Yeah. So now let me summarize. So so these are basically the three important terms. So the first term is the leading term, which goes like f over n to the power d minus 1. So as I was saying, that this term is the analog of beta to the power d minus 1. And then you have a subleading term, which basically depends on the curvature of the spherical entangling surface. So this term goes like n to the power d minus 3. So it's basically compared to this up by n square. And so naively, you would expect that this is the first subleading term, but then there is a catch. The catch is the following, that to define the entanglement, you basically need to regulate the boundary of the entangling surface. So there is a boundary, and so basically you cut out a small tube-like region on the top of the sphere, which has a width epsilon. So you can write down an EFT which has support on the boundary, and these are basically boundary contributions to entanglement entropy. And these are well studied in 1 plus 1D CFT. So you can have these terms also in higher dimensions. So basically this is this boundary term. So you see that integral is happening over one less dimension. And it turns out that this integral is more dominant than the second one. So this is basically the leading term, and this is the first subleading term. So the boundary plays an important role in entanglement entropy. And in 1 plus 1D CFT, this is just a number because this becomes a point. And then this is related, and the reason we use this number g, because in 1 plus 1D, this is related to this entropic g function, which has also monotonic behavior and so on. But again, the main point is that this g, this c1, this f are the same things that appears when you just compute thermal partition function. They are the same quantities. Okay, so, and there are a couple of more points I want to just briefly mention. That so the thermal EFT breaks down away from the limit of vanishing Rényi index, because this expansion only works in the n going to 0 limit, because my temperature, the analog of the temperature was beta was twice pi n. You can, so you might ask that, so there are some other change of variable that you can do, and instead of then hd minus 1 times s1, you basically land up on some d theta metric where you have position dependent temperature. But even all those attempts doesn't really help much, because the point is that, like, if you just naively write down the expansion in the, and this expansion is valid in n going to 0 limit, but if you take infinite, then there is, for example, there is no separation between this term and this term. For example, you see that both terms goes like epsilon to the power d minus 2. So naively you might think that there is a UV regulator, and I can make the UV regulator to 0 and use it as a perturbative parameter. But it turns out that you cannot do that, because this the epsilon appears in the same order for both of these things. So the only way the EFT makes sense is you have to take n going to 0 limit. And I want to emphasize this because this is kind of very different from the 1 plus 1D CFT. It turns out that in 1 plus 1D CFT, the regime of validity is much bigger. In 1 plus 1D CFT, you can actually write down a formula which is universal in the epsilon going to 0 limit for all n. And this is partly possible because of modular invariance. But in higher dimension, this is not possible as of now. In higher dimension, the thermal EFT breaks down. Uh, so in what happens in 1 plus 1D CFT, these terms are not there anymore. The only term is the first term, and the boundary term is a constant. So that's why you are saved. But in higher dimension, this is not the case. There are other terms and they appear in the same order in epsilon. So the only way to control them is to have n going to 0 limit. So this is one thing I want to mention, that in 1 plus 1D, the UV regulator provides a perturbative parameter. One can get the universal result for all values of Rényi index in 1 plus 1D. But in higher dimension, the universality can only be shown in the limit of vanishing Rényi index, which is n going to 0. And then there are some holographic computation by papers by Alex Bellin and Alexander Maloney, where they have shown that even in the holographic context, you would expect that in higher dimension, the Rényi entropy is not universal away from n equals 0. So this is kind of expected also from the holographic side, that in higher dimension, the sense of universality is less than 1 plus 1D. And then I want to just make some final remarks. you can probably extend. So I only told you the story about spherical entangling surface, but I would imagine that if you just do some small perturbation around spherical entangling surface, then the story will go through. And in fact, people have tried people have tried explaining the shape dependence of entanglement entropy, and there are some maps like, so I use this map which takes me from the flat space to the hyperbolic space, and there are some maps available in the literature which basically takes you some small deformation of the spherical entangling surface to some small deformation of the hyperbolic space, and I would imagine the EFT will go through for those kind of things also. So one concrete conjecture or would be that instead of spherical entangling surface, if I take any arbitrary deformation of this thing, then this formula should also be true. And instead of computing this area of del A, I should be computing area of that whatever that surface is. That would be the conjecture, but so far we haven't been able to make it completely concrete. This is a work in progress, and you can also do something called symmetry resolution, which is basically like saying, so this is a concept where is applicable for CFT with a global symmetry. The idea is that you start with a state which is invariant, and then you compute the reduced density matrix on some interval. And because you start with a state which is invariant under the group, the reduced density matrix will have block diagonal structure. So the reduced density matrix will have a structure like this. And then you can ask that how the full entanglement entropy or Rényi entropy gets distributed among various sectors. Because you can always take these smaller sectors and define a new density matrix by rescaling. And then you can define a new entanglement entropy. So roughly speaking, if you have a group G and if the alpha are the irreps, then the blocks are labeled by these irreps, and you can define this Sn alpha, which is the Rényi entropy coming from this irrep sector labeled by alpha, and this is the full Rényi entropy. And you can use the same kind of logic to show that in the n going to zero limit, this difference is universal and only determined by the group theory, where this is the cardinality of the group and this is the scaling, this is the dimension of the irrep. And again, in 1 plus 1D, this equation is true without this n going to zero limit, but in higher dimension we expect it to be true only in the n going to zero limit. And as you can also see that, like here to compute the entanglement entropy, we had to consider some boundary contributions. So you can also imagine there will be many more applications of thermal EFT in the context of boundary CFT. Like you can try to compute the thermal partition function for a boundary CFT, then there will be some bulk terms, there will be some boundary terms, there will be extrinsic curvature, and so on. So there is a lot to do in this context also, in the boundary CFT context. So with that, I will stop here. Thank you.